All right, so the final thing that we need for this course is Stokes' theorem, which is a generalization of Green's theorem. So let's just remember what Green's theorem says. Green's theorem relates the macroscopic curl. So we have a look at a whole function, a whole vector field, and think about how it integrates around a curve. So we have something like f dot dr around a curve. So that's what this bit is here. And how does that relate to integrating the little curls over a whole region R? And remember, this was the k component, because Green's theorem, remember, is for a planar vector field. So f is a planar field, so remember it has an f1 in the I hat and an f2 in the j hat, but no k component. And we've got a region R in the xy plane, and we've got some curve, which is the boundary of that region. So Green's theorem is all about what's happening just in a region on the plane, and you've got just a two-dimensional vector field. And Stokes' theorem is an extension of that to a situation where you have some three-dimensional vector field and you have a surface which is lying anywhere in 3 dimensions, not necessarily flat on the plane. But it looks extremely similar to Green's theorem. So you have the same left-hand side here. Just now, remember that your f is usually a 3-dimensional field. And when we come to the right-hand side over here, we're actually going to work out the curl of f. So that's giving us the kind of little microscopic curls, and we're dotting it with our surface element, so our oriented surface element, which we can think of as this over here. So again, this gives us a way of moving from line integrals to surface integrals. Maybe the line integral is too complicated, you don't want to deal with that, but the surface integral is straightforward, just going to turn it into a double integral, or vice versa. So let's have a look at an example. So we'd like to evaluate the line integral of this vector field. So we can see it's a 3-dimensional vector field, so we're probably going to be using Stokes' theorem. And along this curve, which is the intersection of the cylinder, x squared plus y squared equals 1, and this plane. And we want to orient it so as to have counterclockwise projection onto the xy plane. All right, so let's draw a picture and hopefully figure out what's going on here. So we're in 3 dimensions. So let's have our sketch like this. So the first thing is I want the cylinder that I'm interested in. So that is a cylinder doing something like this. Okay, I've just drawn a couple of cross sections. It has a radius of 1. There's my Z. Okay, so there's my cylinder. And I've got some plane, no idea what it looks like, but it's going to cut the cylinder. So if I think about my plane, I'm going to draw some plane here, doing this. And if you think about how it's going to cut the cylinder, it'll cut it in some sort of ellipse over here. So, and I want to think about the orientation, and I've got my vector field doing whatever crazy thing it's doing. I don't know, all over the place. But I want to find this intersection here. So our C is that curve of intersection, and I want to orient it so that if I project that intersection down onto the xy plane, I get a clockwise projection onto the xy plane. So if I think about projecting my C down onto the xy plane, it's going to be along here. Clockwise means going this way, so up here it's going like so. All right, so what I'm wanting to find is this bunny over here. So let's just write that down. So we've got f.dr. And I go back and I look at that and I say, well, that seems pretty complicated because I would have to parameterize this curve C and then work out dot products and stuff, and that seems like too much work. So would it be possible to use Stokes' theorem? Well, let's have a check. So we need a surface which is piecewise smooth and oriented in 3 space with a normal field n. Okay, well, we do have so what we're thinking about of our surface is this surface here, and that's nice and smooth, and we can find a normal field because it's a straight, it's a plane, so we could find normals to it, so that all works. And a boundary C consisting of one or more piecewise smooth curves, well, we've just got a single nice smooth curve, and it's closed, and we work out the orientation, which we've done, and we need F to be a smooth vector field. Ours is, there's nothing weird going about that. And so we can use Stokes' theorem. So we can conclude that this thing over here, this line integral that we want, must be equal to the integral over our surface. So our surface here of our curl of F dotted with the unit normal of our surface times ds, and that's integral over the surface. Okay, so we need to find a few things. We're going to need to find our ds, which we almost always need to do, and we're going to need to find a unit normal, and then we're just going to calculate everything out. All right, so let's find our unit normal from the surface. Well, we know how to find the normal of planes. We know that our surface is this plane here. So we can find a normal straight off from that. Remember that the normal, though, is just, it can have any length, so we need to find a unit normal, so we're going to need to normalize that. So a normal is, we read off, I'm going to 2 in the I direction plus 2 in the j direction plus 1 in the k direction. So our unit normal will be this thing that we just found, but we need to normalize it by its length. So that's going to be over k over, which is just 1/3, I think. Okay, so we've found our normal. Now we need to find our ds. So this is the scalar ds. So we want to think about our surface as being parameterized as z is equal to 3 minus 2x minus 2y. So we're thinking of this as a g of xy, 3 minus 2x minus 2y. And so we plug this into the formula that we know. We know that ds is equal to 1 plus dg by dx all squared plus dg by dy all squared dx dy. Whoops. So we have ds is equal to, and here again, dg by dx, if we have a look over here, is going to be minus 2, so we square that, we get 4. dg by dy is going to be minus 2 squared, we get 4, so we get 1 plus 4 plus 4 dx dy. So we can put our normal unit vector and our ds together to give us that this thing is equal to 2i plus 2j plus 1k, because this part of the ds is going to cancel with what was in the denominator there. And we need the dx dy. All right, so having worked out all of this, we can put this all together in here. Oh, we need one more thing. We need to work out our curl of f. So let's work out our curl of f. It's going to be the determinant of this thing. What was our vector field? All cubes. Y cubed, x cubed minus z cubed. And if you do all the multiplication out there, you will get 3x squared plus y squared in the k hat direction. All right, so putting that all together, what do we get? We get that the original line integral that we wanted to find, which looked a little bit horrendous, is equal to our surface integral of our curl and then we turn that surface integral into a double integral that we can solve. It's the double integral over our region on the plane of 3x squared plus y squared dx dy. So we need to finally end up, so we've gone from basically trying to calculate a line integral around here to calculating a surface integral on this region down here. And the final thing will be to work out what that is. And hopefully by now you'll look at this and you'll go something like this. We're definitely going to be wanting to use polar coordinates. So we can translate this into the integral over, so we're going a complete way around and there's no theta dependence. So we're going to automatically get a 2 pi from integrating out the theta. And you can translate this into, so this is going to give me an r squared. And if I change this, it's going to give me an r dr. So I'm going to get a 3r squared r dr. And I'm going to integrate from 0 to 1 because my radius is going to start at the origin and integrate up to 1. And so finally I end up with 3 pi over 2. So here we were really using Stokes' theorem to just help us turn something that we couldn't really do, or that would have been complicated and involved a tricky parameterization of an ellipse at an angle, into just a pretty straightforward double integral over a surface that we could do very easily. So as you can see, Stokes' theorem can be used to translate. It can also be used to kind of understand things in the same way that we used Green's theorem. So when you come across Stokes' theorem in physics, it's probably going to be used in one of two ways, either converting into a form that you can integrate, or doing a trick like we did with Green's theorem to help us understand something about a system that we couldn't understand just using the straightforward integral. But I'm not going to do more examples of that. You will see plenty in physics. Okay, so this brings us to the end of the material covered in this course. It's been a huge amount, but I hope what you've realized through the last couple of little videos is that often we use things like our divergence theorem, or Green's theorem, or Stokes' theorem to take complicated integrals and turn them into things that we can solve more simply. So yeah, spend some time practicing how to do your double integrals, do a few line integrals, understand about finding surface elements. So we have two different kinds of surface elements that are just kind of the scalar that we use if we're integrating a scalar field. And then we also looked at the surface elements that we need if we're going to integrate a vector field. So just practice working with both of those. Get comfortable with that and with doing those integrations. We're not going to use parameterization, general parameterizations in U and V. So we'll pretty much always be dealing with integrating over surfaces that are expressed in terms of x and y. And yeah, spend some time. I will put up a mock exam and also some solutions to the tutorials. And yeah, if you have any questions, just email me and I will reply at some point before the exam. All right.